Hi everyone, today we're going to review some topics from Algebra 1 that are going to prepare us to solve quadratic equations. So the first thing that I want to look at is simplifying radicals. And let's talk about what a radical is real quick first. So a radical is this actual symbol that a lot of times you'll call a square root. And it is a square root as long as we are taking the square root, like square root of 9 is 3. But a radical can also be a cubed root. For example, cubed root of 27 is 23 because 3 times 3 times 3 is 27. 3 3's make 27. Or we could even have a fourth root, fifth root. It can go on and on. So the fourth root of 81, we ask ourselves, what can we multiply by itself 4 times? That will add it or multiply to be 81, and that's also a 3 because 3 times 3 times 3 times 3 is 81. We normally don't write the 2 here whenever we have a square root. That's implied. So the actual symbol that we are using is considered a radical, the general symbol. We can call it specifically a square root or a cubed root or a fourth root, etc., depending on which root we're taking. So here we're dealing with square roots, and we want to simplify the radicals, which means we want to pull out any hidden perfect squares that might be there. So in order to do that, we're going to use a factor tree, and we're going to think of 2 things that when we multiply together will equal 28. So a couple of possibilities, but let's go with 2 and 14. And we want to see if either of these is a prime number that can only be divided by 1 in itself, and 2 is a prime number. 14 is not. 14 can still be broken down further, so it can be broken down into 2 and 7. 2 is a prime number and 7 is a prime number. Noticing that I'm circling when I get to a prime number, that means that I have hit the end of the branch, I guess you could call it, on our factor tree. So now I have all prime factors that when I multiply them together will be 28. So I can rewrite this as 2 times 2 times 7. And if I take a look at this 2 times 2, well, that's a perfect square. That's a 4. And if I go ahead and do the operation of taking the square root of 4, I can pull it to the outside and say that the square root of 4 is 2. And then I'll follow that up with the 7 that has to stay under the radical, but I have simplified the radical because I pulled out that hidden square or perfect square. Let's look at the second example. In this one, we have a 68. So 68 can be broken down a couple of ways. Let's do, I know it can be divided by 2 because it's an even number. So I'm going to do 2 and 34. 2 is prime, but I can continue breaking down 34. Oh, let's do another 2. So 2 and 17. Well, 2 and 17 are both prime numbers, so I'm finished with my factor tree. I can rewrite square root of 68 as 2 times 2 times 17. And again, I have a pair of 2's, so I know that those multiplied together is a perfect square of 4, and the square root of 4 is 2. This time, what's left under the radical is a square root of 17, but this is my simplified form. We can also have numbers or negative signs out in front of the square root. We are going to focus on the square root first, but then we will have to deal with whatever is on the outside later. So let's go ahead and look at 60. There are a lot of different possibilities for 60. We could use 2 and 30. We could use 3 and 20, 4 and 15. We could do 6 and 10. There's a lot of possibilities. I want to go ahead and use 4 and 15. And the reason I want to do this is I want to point something out to you. If I happen to use 4 and 15, notice this number right here, this 4. What's special about 4? Well, it is a perfect square. So if I recognize a perfect square before breaking everything down into its prime factors, I can actually just go ahead and use that as my number because I know that the perfect square of 4, when I take the square root of that, I'm going to get 2. Now 15, gosh, that's awfully close to being 16, which is, if you take the square root of that, would be a 4, but it's not. 15, if we broke it down further, would be 3 and a 5, which are prime numbers. So that's not really going to break down anymore. So we could actually just stop with the 4 and the 15, pull the 4 out here as a 2, because the square root of 4 is 2. We still have that negative sign kind of coming along for the ride, and we have our square root of 15. Finally, let's look at 4 and 162. Gosh, 162 is kind of a big number, but I know that 2 has to go into it because it's an even number. So I could say 2 and 81. All right, so 2 is prime, but I noticed something special about the number 81. 81 is a perfect square. It's the perfect square of 9. So I can stop there and go ahead and write my radical as 4, the 4 that was on the outside, and then 2 times 81. And I'm going to pull this 81 out to the outside as, let's see, square root of 81 is a 9. And then I have the 4 that was originally there, and I'm left with the square root of 2 here. 36 square root of 2. Now, if you didn't happen to recognize that 81 was a perfect square, you could have gone ahead and broken it down further. Well, 81 is 9 times 9, and maybe you would have noticed that 9 was a perfect square, and because it's the perfect square of 3, and you could have written it from there. If you needed to, though, just keep on breaking it down. This is a 3 and a 3, a 3 and a 3, and finally I have all of those prime numbers. So again, but if you recognized right here, you don't need to go that far. But if I have a pair of 3s, I know that that's a perfect square. So I could pull a 3 out once and then pull a 3 out a second time. 3 times 3 is this 9 that I already got.